This is the last part of section 11.9, and we're now going to look at components of acceleration. Usually we think of acceleration as a change in speed, but that's typically true when we think of ourselves moving in a straight line. If we're actually moving along a curve, acceleration can happen for two different reasons. It could happen because the speed changes, then certainly the acceleration vector would get longer or shorter. But it could also happen because there's a change in direction. Even if the speed stays the same, the acceleration vector will change direction and then result in actual acceleration. All right, we're going to look at these two things as two parts of an acceleration vector. And so I'm going to go ahead and just say, let's suppose that I've got kind of a generic acceleration vector here. I'm just going to suppose at this point my acceleration vector, say, looks like this. The tangential acceleration component, a sub t, measures the rate of change of speed. So this would be how much of that acceleration is pointing in the direction tangent to the curve. The magnitude of that vector is a sub t. And it's really just the projection, the scalar projection of the acceleration vector onto the unit tangent. We could also say how much of the acceleration is due to a change in direction. That would actually be the projection of the acceleration vector onto the unit normal. We call it a sub n. And our definitions of a sub t and a sub n are right down here. A sub t is the scalar component of the projection of a onto the unit tangent. We can calculate that by finding v dot a over the magnitude of v. And the normal component of acceleration, a sub n, and there is this typo here, is the scalar component of acceleration in the normal direction. And we can find that by taking the magnitude of v cross a divided by the magnitude of v. Now, I haven't actually shown you where those formulas came from. Again, this is just a really long section, so I would refer you to the book if you're interested. But the only thing you'll have to do for my class is to be able to use those. Here's one important relationship. Let's think for a moment about how to write A in terms of its components. It would be the sum of this vector plus that vector. This vector has magnitude at, and it's in the unit tangent or t direction. So I could write it as a sub t times the unit tangent t, magnitude times direction. Plus, I'd have to add this one, which has magnitude an, and it's in the normal direction. So that would be a sub n times n. In actual practice, if you're not using a nice algebraic system like Maple, usually out of everything here, the hardest thing to actually compute is capital N. So oftentimes, rather than go through that whole big long process like we saw a couple of videos ago to find n, people will find everything else in this equation and then just solve for n. Now in our case, since we are allowed to use Maple to help us with the uglier computations, we may or may not use that, but it's just something worth noting. All right, so we'll take these two formulas as givens. And in our example here, we'd like to consider our parabolic trajectory again, t comma t squared, and I'd like to calculate all the values required to fill in the table. We'll then think about the graph and draw some conclusions. So I'm going to do these by hand, but again, they're certainly doable in Maple. We know that we need both v and a to make our computations for a sub t and a sub n. So v would be r prime, 1 comma 2t, and a is r double prime, 0, 2. Let's just go ahead and do the cross, well, we can do both the dot and cross product, I guess. We're going to need them both. v dot a would be 1 times 0 plus 2t times 2, or 4t. And v cross a, since this is a two-dimensional situation, I'm just going to go ahead and put zeros in for the k's. Is 0, 0, 2k minus 0, 0, 0, right? Yep, 0 for everything there. So it's just 2k, or 0, 0, 2. All right, let's come up with some formulas for the tangential and normal components of acceleration. A sub t is supposed to be v dot a divided by the magnitude of v. We already did v dot a right here, it's 4t. And the magnitude of v is our famous 1 plus 4t squared that we got so tired of a couple of videos ago. That can't be simplified, so I'm going to leave it just like that. The normal component of acceleration is the magnitude of v cross a over the magnitude of v. So the magnitude of that cross product, that's just 2 units up the z-axis, so it's just going to be 2, right? You can put the formula in if you want to, but we don't really need to. We can see it. And again, the magnitude of v is the square root of 1 plus 4t squared. All right, I'm going to go ahead and I'm going to calculate AT and AN at a few different values of t. So just to make that go a little bit quicker, I'm going to put those in my calculator as y1 and y2. y1 is going to be the tangential, just so I don't forget. I'm going to mark them. y1 I'm going to put in as the tangential component. And y2 I'll put in as the normal component. All right. In my table, I'm going to start by filling in these two. So let's see here. A sub t at negative 1 is negative 1.79 approximately. Oops, 7. And y2 is the a sub n, that's about 0.89. At 0, I get 0 and 2. And at 1, I get positive 1.79 and 0.89. One other thing that's listed here, and that's the speed. Speed, of course, is just the magnitude of the velocity vector. So I'll just mention down here somewhere speed, magnitude v, is just the square root of 1 plus 4t squared. And we should be able to do that pretty easily in our heads. If t is 1, I would get the square root of 5. If t is 0, I'm going to get the square root of 1, which is 1. And when t is positive 1, I get the square root of 5 again. All right, I'm going to sneak actually right over in here because I'd like to talk about it while I can see this table. I'm going to sneak in a little picture. This is certainly a parabolic trajectory, t comma t squared. And the 3 points that I was interested in were when t is negative 1, I'd be at negative 1, 1. When t is 0, I'd be at 0, 0. And when t is positive 1, I'd be at 1, 1. Oops. Gotta be on the curve, Christy. Let's try that. Better make that my 1. Get rid of that so it's not distracting us. All right, that is t equals 1. So let's think about this for just a minute. And I keep doing this, but I shouldn't. This is a directed curve, so I really shouldn't be going this way. From smaller t's to larger, we're really always traveling in this direction. Okay. So do these make sense? Let's see, the tangential component of acceleration is negative here, and that's because the speed would be decreasing. Imagine yourself driving along this path. You're coming in toward a tight turn, right? Your speed's going to decrease. Right at 0, the tangential component is 0. There's no change in speed at all. Instantaneously, our speed of 1 is just constant. And then after we make the turn, we can speed up again. And notice the acceleration here is positive. Speed's getting larger as we come out of that turn. So a larger speed becomes smaller, negative acceleration, and then it gets bigger again, positive acceleration. What about the a sub n's? Well, let's see here. That's the acceleration due to a change in direction, and it was largest at t equals 0. Does that make sense? The direction is changing all the time, so I always have a non-zero value of a sub n. But the direction is changing fastest right here at the origin, which is also the vertex of the parabola. Also where the curvature is largest, right? Those things are all related to one another. All right, so that's our components of acceleration, and that wraps up section 11.9.